Hey, science fans, let's talk about something incredibly small but monumentally important. They looked at a rock and asked, if I cut this rock in half and then cut that half in half and keep cutting it, will I ever reach a point where I can't cut it anymore? One group of thinkers, led by a philosopher named Democritus, came up with a radical idea. He called this particle atomos, indivisible or uncuttable. Other very famous philosophers like Aristotle had a different idea. He believed all matter was made from four basic elements: earth, water, air, fire. Because Aristotle was so influential, his four-element idea dominated scientific thought for nearly 2,000 years. The concept of the atom was mostly forgotten, waiting in dusty pages of history. But the seed of the idea was planted. It took until the early 1800s for someone to pick up where Democritus left off and give the atom a scientific comeback. This is where our modern atomic journey truly begins. Fast forward about 2,000 years from ancient Greece to the early 1800s. Enter John Dalton, an English schoolteacher and scientist. Dalton wasn't just thinking about stuff, he was experimenting with it, especially gases. He noticed elements always combined in fixed whole number ratios. For example, when you make water, it's always 2 parts hydrogen to 1 part oxygen. First, all matter is made of tiny, indivisible particles called atoms. Second, atoms of a given element are identical in mass and properties. Atoms of different elements are different. Finally, chemical reactions happen when atoms are rearranged, combined, or separated. So, what did Dalton's atom look like? It was a simple, solid, indestructible sphere, a microscopic billiard ball. Dalton's theory wasn't perfect. We now know atoms have subatomic particles and isotopes, atoms of the same element with different masses. For nearly 100 years, Dalton's model was the best we had. Physicists were playing with electricity and a fascinating piece of equipment called a cathode ray tube. A cathode ray tube is basically a glass tube with most of the air pumped out, and 2 electrodes inside. When you apply a high voltage, a glowing beam shoots from the negative cathode to the positive anode. J.J. Thomson brought a magnet near the tube, and the beam bent. Using electric and magnetic fields and measuring the deflection, Thomson calculated the mass-to-charge ratio of the particles, much lighter than any atom. He found they were about 1,800 times lighter than a hydrogen atom. Thomson had discovered the first subatomic particle, the electron. This discovery shattered the idea that atoms were indivisible. Thomson next proposed a model to include these electrons, a model we'll call the plum pudding. Thomson proposed what has become famously known as the plum pudding model. He imagined the atom was like a sphere of pudding with negatively charged electrons embedded like raisins. This explained how atoms could be neutral overall, the negative electrons balanced by a diffuse positive charge. It predicted that fast particles should pass through with only small deflections, like a bullet through smoke. For a while, it fit the data and guided research, but it was just a stepping stone. Soon, experiments would test this prediction in a dramatic way. Thomson measured a mass-to-charge ratio, but he didn't know the electron's charge or mass separately. Robert Millikan took on the challenge. He built a chamber with 2 parallel metal plates and sprayed a fine mist of oil droplets into it. Some droplets picked up static charge. He watched a single droplet, timed its fall, then applied an electric field to suspend it. By adjusting the voltage until the upward electric force balanced gravity, the droplet hovered. Knowing the electric field strength and the droplet's mass, Millikan computed the drop's charge. He repeated this for many droplets and saw each charge was a multiple of a single tiny number. He found the fundamental charge was about 1.602 x 1019 coulombs, the charge of 1 electron. With Thomson's MQ and Millikan's charge, the electron's mass was determined, a constant of nature. With subatomic particles measured, the next big test of atomic structure began. Ernest Rutherford, an expert in radioactivity, used alpha particles to probe the atom. He fired these tiny, dense, positively charged particles at an ultra-thin sheet of gold foil. If Thomson's plum pudding were right, the alpha particles should pass through with only small nudges. Geiger and Marsden performed the test with detectors to record where particles landed. Most particles, over 99.9%, zipped straight through and hit the screen on the opposite side. Geiger and Marsden recorded these results meticulously, but when they checked detectors to the sides, something impossible showed up. About 1 in 8,000 particles was deflected at very large angles. Even stranger, some bounced almost straight back as if hitting a solid wall. The plum pudding model could not explain these results. Rutherford reasoned the positive charge and most mass must be concentrated in a tiny, dense center, the nucleus. If an atom were a stadium, the nucleus would be a marble in the center. Rutherford proposed a new model, a tiny, dense, positively charged nucleus with electrons orbiting around it, like a miniature solar system. This explained why atoms are mostly empty space. Most alpha particles pass through the void. But classical physics said orbiting charged particles should radiate energy and spiral into the nucleus. Yet atoms are stable. This contradiction meant Rutherford's model, while correct about the nucleus, couldn't explain atomic stability. A missing piece remained, something to explain why electrons don't fall in. Bohr would provide that piece. Next, Niels Bohr and the idea of quantized orbits. Niels Bohr came along in 1913 to solve why atoms are stable and why elements emit light at specific colors. A planetary model where electrons could orbit at any distance couldn't explain these quantized spectral lines. Bohr proposed electrons occupy fixed orbits, specific energy levels, like rungs on a ladder. As long as an electron stays in one of these orbits, it doesn't radiate energy and won't spiral into the nucleus. When an electron jumps between levels, it emits or absorbs a photon, whose energy equals the difference between levels. This explained the fixed spectral lines. The energy differences are fixed, so emitted colors are fixed. Bohr's model was a stunning success for hydrogen, but it was a stepping stone to full quantum mechanics. We now understand electrons as probability clouds rather than neat orbits, but Bohr's quantization idea was crucial. Let's look back. Dalton, the billiard ball, Thomson, electrons and the plum pudding, Millikan, measured electron charge, Rutherford, nucleus and empty space, Bohr, quantized energy levels. This journey shows how science builds, test, revise, and refine. Each model answered questions and opened new ones. And that, my friends, is science.